A huge thanks to Brian for sponsoring this video. Good morning, fellow mathematicians, welcome back to another video. Today we are going to find the determinant of this matrix right here. And I know what you are thinking right from the thumbnail. Papa Flammy, the fuck is this? We are so cooked. But I think I got a plan. I found this problem over on Facebook, implying we discuss mathematics or actually good mathematics problems, not certain, but I think I found a solution. I checked with the solution from OP and at least the final solution is correct. I have no freaking idea what OP did over there. Some weird Indian stuff. He did some seriously weird stuff. I have no idea what he did, but we are going to do it by the principle of mathematic induction. And I hope you are going to enjoy the video. By the way, this video has been sponsored by the wonderful people over on Brian. They provide a great service to the STEM community. Wait until the end of the video to learn more. Thanks for sponsoring, and now we are going to dive right in. Now, we're going to make this mathematically correct at first. Determinant of this thing, and as mentioned before, mathematical induction, because that's the first thing I came up with. We have an n by n matrix indicated by an with the index n here, and it's a square matrix where, if we observe the matrix, we have 3 on the main diagonals, and on the non-main diagonals we have 2, 1, 2 and 1, 2, 1 alternating all the time. So at first we're going to try to spot a pattern, and once we do that we're going to prove that the pattern holds by mathematical induction. And we're going to check for all real numbers, not real numbers, natural numbers, I'm terribly sorry. There is actually real number induction, but that's for another video. So at first we are going to start with A1, which is gonna be our base case later. If we take the determinant of A1, that's just a 1 by 1 matrix, so that's the determinant of 3, or that's the value which is just 3. Okay, that was very hard indeed. Now what about A2? Now this is where the fun begins. We are going to see A2 is just a 2 by 2 matrix, so it's just this block up here with 3 on the main diagonals and 2 and 1 here. How do you get the determinant of a 2 by 2 matrix? You multiply those diagonals together and then you are going to take the difference of those. So 3 times 3 is 9, minus 2 times 1 is 2, which is 7. Okay, perfect. Now what about A3? And this is where we are going to start seeing a pattern. So A3 is this matrix right here. So the determinant of 3, 2, 0, 3 on the main diagonals, 1 here, 1 and 2 and 0. We're going to make use of the rule of Saru. You could also use the checker pattern, you could say, which you are going to do for the huge case, you could say. But for now, rule of Saru, because it's easy to remember. Just multiply all of those diagonals together, add those, and then we are going to subtract the multiplication of all of those diagonals. It's as easy as that. So 3 times 3 times 3 is 27. 2 times 1 times 0 is 0. 0 times 1 times 2 is 0. So the addition part is done. So subtraction. 0 times 3 times 0 is 0. Then we have 2 times 1 times 3, which is 6. And then 3 times 1 times 2, which is 6. Giving us 27 minus 12, which is 15. And this is where I already spotted a pattern. Do you see something? Well, those are just powers of 2, but subtracted 1. So this right here is nothing other than 2 squared minus 1. This right here is 2 cubed minus 1, and this is 2 to the 4th power minus 1. So we could make an educated guess right here, and this educated guess would be that if we have an, then the determinant of an is going to be, so we have A3, 2 to the 4th power minus 1, 2 to the n plus 1th power minus 1. And this we are going to suppose. This right here is going to be our induction hypothesis. We are going to suppose that for all n out of the natural numbers, right before n plus 1, it holds that the determinant of an, that's what we are going to suppose, is equal to 2 to the n plus 1 minus 1. Induction hypothesis and also base case. We have a few base cases. Now we need to prove this using the induction step, meaning we are going to take a look at an plus 1 and we are going to somehow include our induction hypothesis in there to prove that this actually holds for all natural numbers n. This is how induction works. So let us go ahead and get started, and let us write out an plus 1 at first. And an plus 1 honestly just looks the same as an. That's all there is to it. The only thing that really decides if it's an even or odd number is if there's 1, 2 here or 2, 1. So let us just write an plus 1 out yet again. And this is going to result in the determinant of 3 on all main diagonals. Then we have 2, 1, 2, and so on here, 3 down here. And we have 1, 2, 1, and so on. And there are zeros everywhere else. Doesn't look nice, but it just is what it is. It ain't a beauty, but it's our beauty at least. Okay, now here comes the checker pattern part. If you want to get yourself the determinant of any n by n matrix, what you're going to do is you're going to place a checker pattern on here. Just use any column or line, whatever you wish, and do plus, minus, and so on. There are zeros here everywhere. And then what you're going to do is, if you take the 3 right here, you're going to multiply this entry with the matrix which is going to be left once you cover up all the other stuff, which is on the same column and line as the number that you basically introduced here. So covering all of this up leaves us just with basically this matrix right here, which is going to be an n by n matrix because we're going to reduce the dimension by 1 from n plus 1 to simply n times the determinant of the matrix 3, 1, 2, 3, 1, 2, 3, and so on, 3 and zeros everywhere else. And then we are going to continue with this pattern, but this time we are going to take -2 because we have put the negative sign here. So -2 times the determinant of, and now we are going to cover everything up. We are going to cover this whole line up, and we are going to cover this up, leaving us with 1 and then all zeros on the first column. So 1, 0, 0, 0, and so on. And what else is going to be left? We are going to have 1, 0, 0, 0, 0 all the way over here. We're going to close this up. And if we cover this up more, we are going to have, as the last block left, basically just our regular all matrix pattern once again. So we are going to end up with 3 and then, let me see, covering this up, 3, 2 is here, 1, 3, 3, and so on, with 3 down here. That's a bit of a mess, but it's not that hard actually. You just need to write everything out nicely. Now what I noticed here immediately, this right here is an n by n matrix. And this right here looks eerily similar to our original matrix that we had right here. Just take a look at that. What is the only thing that is really different here? The only thing that is really different here is that 2 and 1 is switched to 1 and 2. So basically what this matrix right here is just this matrix, but reflected right at the main diagonal. That's just a transpose. This thing that we have right here is an, but transpose and the determinant of that. Now, remember the checker pattern that we just did. If we suppose that the determinant of an is 2n plus 1 minus 1, we could determine this determinant by using the checker pattern on this column right here. So plus, minus, and so on. But we could also determine it by doing the checker pattern here, plus, minus, and so on. Now, if we were to do the checker pattern on this column right here, this would be the same as doing the checker pattern on this line right here. What I want to say with this is that the determinant of the transpose matrix is the same as the determinant of the regular matrix. So this right here is the determinant of an. And this is where our induction hypothesis comes in, because we suppose that the determinant of an is equal to 2n plus 1 minus 1. So that is the first key to success here. So we are going to end up with 3 times 2 to the n plus 1, where we have officially used our induction hypothesis in here. But we are not done yet. Because what we still have is this matrix over here, where we need to take the determinant. And well, it just is what it is. Let us move on with the checker pattern. So plus, minus, and so on. But it actually ain't that bad. Because if we take a look at this part right here over here, I have suddenly stopped. I didn't continue with the checker pattern. Why is that? Because we have plus, minus, and so on with all zeros. If we were to take this matrix behavior right here for the determinant, we have 0 times the rest of the determinant, which is just 0 because the determinant is a real number, and all of those zeros and so on. So this determinant is actually going to be cancelled right at the 2. And this comes to our advantage right over here. So we are still going to have another determinant, but after that, it's actually quits. Because if we do that, we are going to end up with -2 times the determinant of 1 times the matrix, which is still left here, basically. So let us continue. We are going to get -2 times. Then we are going to have 1 times the determinant of 3, 2, 1, 3, and so on. So 3 on the main diagonals and so on. And then we are going to have 2 and 1 and 2 and 1 and so on. Zeros in all the other places. And then we are going to have -1 times this part which is still left over here. It's kind of hard to see. Take a piece of paper, do it for yourself. It's a bit messy because it's a huge matrix overall. So we are going to have -1 times the determinant of the matrix. And what is still left is, if we cover this line up, we are going to have zeros in an entire column. All zeros here, and then we are going to have a bunch of stuff over here. So we are going to have 2, 3, and 1, and then 3s, and so on, with zeros everywhere here. And this is exactly what I said a second ago. Suppose we are going to determine this determinant over here. Now, if you do the checker pattern here with plus, minus, and so on this entire column right here, what is going to happen? We have 0 times the determinant, plus or minus 0 times the determinant, and so on. This overall here is trivially equal to 0. Try it out with a lowercase, for example, A4 or A5. That is already sufficient. You are going to spot that at the second iteration, it's already going to come to a complete halt. Doesn't matter if you do this general case right here or if you do a smaller case. You're going to notice that it's going to stop immediately at the -1 here. So the only thing that we need to lastly evaluate is this part over here. And this part over here is just gonna be an n -1, because dimension here was n, dimension here was n, we're going to reduce it by n-1. So this right here is an n-1 times n-1 matrix, and it's exactly of the form as basically this original matrix that we have right here. So this thing that we have right here is nothing other than an-1. And by our induction hypothesis, we did suppose that the determinant of an and everything before that, so an-1 and so on, abides by this pattern that we have right here. So by the induction hypothesis yet again, we are going to have that the determinant of an-1 is going to be equal to 2 to the, okay, for n-1, the n plus 1 minus 1 is going to be 2 to the n minus 1 overall. So where are we at right now? This part right here is going to vanish. We have this part over here, and we have -2 times 2 to the n minus 1. I'm going to write everything out over here. So what we are going to get conclusively is 3 times 2 to the n. Let me see for a second. 2 to the n plus 1, and then this was a 2 to the n matrix, right? I was tripping here. We have 2 to the n plus 1. Yeah, I'm terribly sorry about that. There was probably an annotation here. there was my mistake. So we have 2 to the n plus 1 minus 1, and then we have negative 2 times 2 to the n minus 1. This is where we are at, and it was scary at first, but it actually panned out very nicely. Now let us try to simplify this a tiny little bit. So by multiplying everything out, we have 3 times 2 to the n plus 1 minus 3. Then we have negative 2 times 2 to the n minus 1, but 2 times 2 to the n is the same as 2 to the n plus 1. Yeah, I'm gonna write it out. This is 3 times 2 to the n plus 1 minus 3 minus 2 to the n plus 1 minus... No, this is negative 2 minus 2, which is going to be plus 2 overall. So we are going to get plus 2 over here. And now it's time we simplify everything a bit more. So we have 3 times 2 to the n plus 1, and we subtract 1 times 2 to the n plus 1 from it. So what we are going to get overall is 2 times 2 to the n plus 1, and then we have negative 3 plus 2, which is minus 1, which is very good because we need a negative 1. Now the only thing that we need, because this right here was the determinant of a n plus 1, is a term of 2 to the n plus 1 plus 1 overall. And just look at that. This is 2 times 2 to the n plus 1. By using exponentiation rules, this is the same as 2 to the n plus 1 minus 1, which is going to be the determinant of a n plus 1. And this right here was our inductive step. We have done it. Do you see this? We get from the determinant of a n is equal to 2 to the n plus 1 minus 1 to the determinant of a n plus 1 is 2 to the n plus 1 plus 1. This is what we did. We just increased n by 1 minus 1. So by using the principle of mathematical induction, we have successfully proving by also pattern spotting, I dropped my chalk, that the determinant of this, whatever the hell this right here is, matrix, is equal to 2 to the n plus 1 minus 1. Which is pretty cool, don't you think? Did you find out the solution? Let me know down there in the comments below. And if you want to see more mathematics, physics, computer sciences, really doesn't matter, anything in the STEM universe, you could say, then the contents of today's sponsor Brilliant might be the perfect fit for you. Woo! There was a lot of determinants and determine. English is a hard language, but equally hard can be linear algebra. I remember back in my first semester at university, we got to generalizing matrices and the like. And it was a bit of a hassle, pretty abstract at some point, especially when it came to vector spaces. But in this day and age, you don't need to worry about the abstract stuff as much anymore as I did back then, because there are a lot of resources out there, like Brian, who make life a lot easier for you, especially when it comes to everything in the STEM field. Brilliant is your source for some of the best online learning content that you can find out there on the internet. As mentioned before, don't worry about the abstract stuff. Brilliant makes it rather easy for you to learn something new on a daily basis, be it at home on your computer or on the go using their app, by doing their online courses, which really focus on the visual side of learning. Take determinants. There's actually a very nice visual interpretation behind determinants, as for example areas or volumes of bodies, for example. And Brian in their linear algebra course introduces vectors at first and all of this stuff, and then basically they combine vectors together, they smash them together to get yourself determinants, and now you have a three-dimensional coordinate system, for example. And with all of their great visuals over there, visualizations and everything else that they have, their graphics and the stuff that you can play around with, they really make it easy for you to get a hang of linear algebra in no time at all. And it's not limited to linear algebra. There are other really hard parts of mathematics like stochastics or abstract algebra, which are way easier to understand once you grab your mouse and you grab the graphics over on Brain and play around with those up until you notice that groups are just generalized symmetries, for example. Play around with the snowflake over there or this virtual Rubik's Cube. They really provide a unique service to the STEM community, which I highly appreciate and that I really love to advertise to you here over on this channel. Don't take my word for it. Just take a look at any of the things that I have here on screen. It's seriously appealing and it's a lot of fun to play around with everything over in their courses. Just try it out. Use my link down there at the top of the description or the QR code somewhere up here in the corner, Brain.org/FlammyMaths. With it, you are going to get free access to the whole landscape of Brain. Try it out, see if it's something for you. And if you have the feeling that you want to see more, that you want to do more, that you want to use Brain in its entirety, then definitely make sure to make use of my link in its entirety and get 20% off an annual premium subscription. It's seriously cool what they offer over there. It's a unique learning concept which really makes it accessible to most people. Learning can be fun. It doesn't need to be abstract or hard at all. I use Brain at school too to show them visual proofs over, for example, in my geometry course. Just give it a shot, see if it's something for you, and if it is, then use the link and support the channel this way, big time. Thank you guys for watching. If you enjoyed today's video, then make sure to subscribe or become a Patreon supporter to help keep the channel alive. And up until next video, I wish you guys a fabulous day. See ya.